Okay. Hello. Alright. So today I'm gonna do some math. Right. Okay. So we have find the period and graph the function y equals 1/2 tan x. So we know that tan has a bunch of stuff like that. And then you go like this, and you go like that, and then you go like this to the other asymptote. That's what it looks like. So what we're gonna do is we're gonna do this. Basically, this should, if this was a cosine or a sine graph, it would have been the amplitude. But in tan, amplitude is kind of strange. We're gonna take a look at this. Okay, so we have a line, and it's gonna be our y-axis, and then we're gonna have our x-axis. Wonderful, isn't that great? Okay. All right. So the period is pi. We know that because we done this in class, I guess, maybe, probably. Pi, what does that mean? It means somewhere over here where there's pi over 2, we have our first asymptote. And then when there's pi, there's our second asymptote. Right? So we're gonna have this, and then we're gonna have this, and then this is going to go on until 3 pi over 2. And then we're just going to keep on doing what we're doing. Alright? This asks for this thing. So, basically, this would look a bit more squished. And let's see if that's true. We have 1, and we have 1. Let's do half. 1 over 2, 1 over 2, this is negative, this is a 2, 1. Actually, it should look something like that. This should be 1/2. It should be negative 1/2. Something like that. Okay. If we have something like that, something like this, there should be the curve thingamajig, the curve around these parts. You see, when it goes like that, when the tan graph goes like that, you got something like that, and you need something like this, right? Somewhere it goes like this, right? Somewhere along the line, it's going to start curving, going towards that asymptote, right? If we have a unit circle, we make ourselves a unit circle, right? Tan is, we know this, tan is undefined around here and around here, right? Because it's cosine, no, rather it's sine over cosine. Now, if cosine is 0, right, and that happens here and here, that happens here and here, when cosine is 0, it doesn't matter what sine is, right? It'll make that undefined, and that's why we have the asymptotes, right? If a radius is just 1, then that's the normal graph. If it's 1 over 2, then if it's 1 over 2, and then if 1 was, oh, no. If 1 was something like, I don't know, circle around that. Let's just say this is 1. Right? That's what it would be. Shouldn't be much different. If this was, if this is what that's like. And if this is negative pi over 2, and what we can do is we can make something like this, where it's sort of more squished here. So it's like this and like this. Is that right? I don't know. Probably. It's probably right. I think it's right. See, that's what I think it should be. And it probably could. Would that mean that it takes more, I don't know, there's more space here until it gets there, right? Because you're just squishing the graph, because that's what amplitude is, right? It's stretching or compressing the graph vertically. That's kind of what we did here. So we went from this to something like this, but the asymptotes are the same. Nothing changes except a couple values in the middle here. I don't know why it keeps doing that. Nothing changes. Nothing changes except for some stuff here. This takes, I don't know if it's a bit steeper, and this, it's less steep. Okay, good job everybody. Next we're gonna go to the next problem. Alright, next problem. This one is a bit more interesting, and it's because we've got actual, we don't have to deal with no amplitude, alright? We got to deal with the other stuff, and that matters. Okay, first let's find the period. Period is, no, it's pi. It's pi over 2, because this is 2, and the period for the parent graph, which is, this is the period for y equals tan of x. That's what this would be. It's just pi. Pi over 2 is what we're looking for here. This would basically mean a shift to the left That's what I think, at least. It's probably what it is. Again, we have our little graph here. If we do that, our asymptote has to be at pi over 4 and pi over 2, and all those increments around that. So pi over 4, we can put that there. Pi over 2, 3 pi over 4, and then pi. Right, okay. I'm gonna go for pink lemonade look. And then again. Oh, no, that's not what it is. Like, our asymptotes happen around these things. This is just where, at this point, when the x value is any multiplier of pi over 2, which is the period, that would make that's when this point should actually be here. You know, that's when the graph meets. That's when the graph of tan, when the function meets the x-axis. At least that's what I think. Okay, that's the normal graph. This should be like that. Pi over 4. Right, and then we go back like this. Oops, went too soon. Go like this. Pew, like that. Some sort of shape like that, you know, whatever. This point's going to be negative pi over 2. Is that what we're looking for? Not exactly. That's what we've drawn is the graph for y equals tan 2x. What we're looking for is a shift of pi over 2. And what does that mean? Basically, if we're going to move it pi over 2 to the left, we're going to have to do that because it's a plus here. We're going to do that by seeing this is pi over 2. I mean, this is 0. This is pi over 2. So whatever's here should be here, right? So we're just going to shift everything this way, and it seems to be the same, right? It seems to be the same. Drawing that there. I think that's right. I could be wrong, but I don't think I'm wrong. Right? You just shift this here, and you just shift the entire graph, an entire period, to the left. And if you shift any graph by its period, any function here by its period, then really you're not changing the graph. This, these are the same. This is the same as this, right? Okay. Are we good? I think we're good. Yeah, these are pretty much the same. So if our period is pi over 2 and we shift pi over 2, it doesn't matter if it's to the right or to the left. It's going to be the same as y equals tan 2x because you're shifting the graph by its period. Shouldn't look any different. It should look the same. Okay, moving on to the next question. Alright, so this question says, the beam from a lighthouse completes one rotation every 2 minutes. At time t, the distance d, shown in the figure on the next page is where, it says next page, but I condensed everything here. Shown in the figure is where t is measured in minutes and d in miles, right? This is d, and this is another d, a distance, right? We're trying to find d of t, right? When the time is a certain amount of time, how far do you get, right? Okay, so I've just set up these three things. This for this, this for this, this for that, and we're just gonna use our calculator. All right, we're just gonna use our handy dandy calculator. I'm gonna plug in 3 tan pi 3 tan pi, hold on, pi times 0.0.15, and that gives me, I'm doing degrees, but that gives me 0.0246 something. Maybe we should do B first, right? If we want to sketch a graph for this, well, this doesn't really matter. Like it makes barely any difference, hardly any difference, as we found out in the first problem. Really, what we're looking for is what this does, because that changes the period of the graph. And we find period by doing period of the parent graph over k being this thing. In our case, it's pi over pi, and the period is 1. What does that mean? Let's find out. If we draw something like this, right, and we have 1, 2, 3, for example, that would mean that you'd have an entire tan graph in this, right? And that would also mean that tan would meet the graph at every 0.1 increment away, right? Why is that? Because the period is 1. That's why. That would mean that our asymptotes have to be in the middle, which would be, and they would be 1 over 2. That would mean 3 over 2. And this would be 5 over 2. 5 over 2, right? And t t is over here, right? This would be t. This axis. That's t. So we just have to find when t is somewhere around here, right? We know the first one is 0.15, so guessing somewhere around, no, it's guessing is somewhere around here. The other one is 2.5, so somewhere around here. The other one is 4.5. If this is 1/2, then it should be like right there, right? It's like very close to it. It's basically 9/20ths, which is close to 10/20ths, which is a half, right? So maybe, so I mean, if these are the asymptotes, oops, these points are the asymptotes, right? Then what we would have basically is a graph that looks something like this. Right? So this actually shouldn't cross. That's not what it should have. That's no. Okay, that's just wrong. Wrong. We have this blue line. I mean the graph should just almost touch 1/2. What does that say about these? Well, we know d of 0.45 is very, I mean, it's close to infinity, I guess, in terms of its y value. And we're looking for the y value, and we're looking for d. So let's try this one first, right? Yeah, and I guess that answers C, right? What happens to the distance d as t approaches 1/2? Well, as t approaches 1/2, this is x, which is t. Like, we're measuring for t here, and we're measuring for d here. So when t reaches near 1/2, or 3/2, or 5/2, right? It's the d value, the y value, distance d is near infinite. You know, it's very close to, it's close to infinity. It's not quite there, but it's almost there. But it's never gonna, like, it's gonna be undefined if t were to actually be 1/2. So how about we take our handy dandy calculator and we find out this one, the last one, right? Why don't we try that? So we have 3 tan pi times 0.45, and I got 0.03, I mean 0.074037058. Is that right? I don't know. I don't know. I mean, let's see if x is equal to 0.45, what would that equal to? I don't think it should be. I think I must have done something wrong, because it should be greater than 1, right? Way greater than 1, right? Because it's stretched out. Let me get my graphing calculator. Or we can just do this on Desmos. Let's use the graphing calculator. Firing up the TI Inspire. Anyway, this should probably be up here. This value. This value, it's like here, and this is like near 0, right? This should be around 1, 0.25 when t is 0.25. Let's see. Oh, my calculator needs charge. Isn't that great? Well, I guess we could use Desmos. Let's have x be equal to 0.25 and x be equal to 0.15. Actually, 0.25 would have been 1 if our amplitude, or whatever this is, if that were 1. But since that is 3, we have to multiply it by 3. So d at this point d would be equal to 3. This we know, because 0.25 is half of half. You know, a fourth is a half times a half. And since our period is 1, then, and since there are 4 quadrants, you know, that means when we're at 0, basically, or when cosine is 1, and when cosine is I think root 2, and when sine is root 2, we get 1, right? And then since we're multiplying it by 3, right? If we have a unit circle, looks like that. Right here, this was a unit circle. Radius would be 1. You stretch that out, radius should be 3. So that's what it is. Okay. So this we know has to be greater than 3, and this we know has to be less than 3. Well, let's see what it is. So we have our handy dandy calculator, and we're gonna graph f of x equals 3 tan. I'm gonna put a pi of x. Keep saying I'm missing parentheses. Tan of pi. So let's see when let's just go to menu. No, let's go to menu actions. Let's just press tab. Let's go to calculator. Solve. Solve parentheses. 3 tan pi t comma t, and we should get 3. Alright, this is confusing. This should be 3, and we know that this has to be less than 3 and this has to be greater than 3. How do we figure these two out? Well, that's the question, isn't it? Well, let's go to Desmos then. In Desmos, it says that when x is equal to 0.15, y should be 1.529, and 1.529 over 3 is about a bit more than half, and that's what it should be, because 0.15 over 25 is, 0.25 is 0.6, and of course they shouldn't exactly be the same because the tan graph stretches, so it makes sense. And Desmos, when I graph this in Desmos, it now says that when x is 0.45, y is 18.941. I just don't know how you would solve this without a calculator. I don't know if you're like super ooper duper ooper schmooper smart. This should equal to 18, near 19, 18.9, about. And this should equal to 1.529. So around 1.5. This is the only one that we can solve without a calculator, I think. Right? Yeah, that's all there is to it. I think that's it. Well done, folks. You did great. We did a lot of math. We did some math. Nice job. Try this at home for yourself. I may be wrong in my process, but my answers are probably right. Okay. Until next time. That's it, folks. Yay. Do-do-do-do. Do-do-do-do. Do-do-do. Do-do-do-do-do. Do-do-do-do-do. Outro theme song. Okay. Until next time. That's all.